I do have a question.
Sure.
Would it be possible for you to go over question 10 and 12 on chapter 4.3?
10 and 12 on 4.3. Um, let me check what those are really quick. Are those GCD questions? 10 and 12 on 4.3. And 12. Yeah, these are some more interesting questions. I think I'd be happy to discuss these in office hours right after class today, if that's all right.
Okay.
Yeah. So I think 10:20 or 10:30, I'd be very happy to discuss these fun problems. All right. The next midterm, when is the next midterm? It's not this week. I would guess the next midterm is, gosh, maybe the 9th? The 9th seems reasonable. I'll send out an email. Any further questions? Hopefully
I have
it
a quick
is.
question.
Yep, sure.
So, you said in one of your lectures that we could turn in a perfect math or the second exam for half the credit. Is that by the last day of class, or is that by the time of our final exam?
Let's do last day of class.
Okay. Do you know when our final exam is?
I believe it's the 19th at 8 a.m. But you'll have to check. That knowledge wasn't available to us at the beginning of the semester, so it's not in the syllabus, but you can look it up.
Okay. All right. Thank you.
Yeah, sure. 19th at 8 a.m. Look at that. I was right. We're almost there. My word. My. I want to start on some GCD and LCM stuff and finish off this number theory chapter. GCD and LCM. Okay, so let's start with a definition. So if A and B are positive integers, then the largest integer, D, such that D divides A and D divides B, is the GCD, greatest common divisor. AKA GCD of A and B. It is written either GCD of A and B, or sometimes, if I'm being a little lax, even just writing in parentheses A comma B. This notation kind of messes with this is kind of using notation that we've already used for something else, but in this context, it should be clear. So I think y'all are familiar with GCD, I would guess. Yes, no, maybe? Great. Let's do some quick examples. For instance, what is the GCD of 18 and 24? Just for fun? 6. Yeah, I tend to agree that this is 6. What's a good way to see that it is 6? Well, it's okay if we just know that it's 6. The only divisors of 18 that are bigger than 6 are 9 and 18, but neither 9 nor 18 divide 24. So that's kind of a quick check. How about the GCD of 17 and 24? Yeah, this is 1, exactly. There is no number larger than 1 which divides both 17 and 24. And the way to see that is 17 is a prime, so its only divisors are 1 and 17. And 24 is not divisible by the prime 17, so it's got to be 1. Okay, let me give you a hint about a good way to think about GCD. Let's consider the following numbers. A is equal to 2 cubed times 3 squared times 11. And B is equal to 3 times 11 squared times 13. This is a way that I can write numbers, right? We know from the fundamental theorem of arithmetic that every integer has a unique prime factorization, and here I've given 2 prime factorizations. Now what is the GCD of A and B? Yeah, it's 3 times 11, or 33. Can you tell me why that was a natural choice?
Because 3 and 11 show up in both A and B at least once.
That's right. And another thing is, so the way that I like to think about this is that if you want to divide a number, essentially what that means, like if D divides A, then if A has some prime factorization P1 to the A1 all the way out to PK to the AK, D must have a prime factorization where, first of all, D is equal to, say, Q1 to the D1 all the way up to Qn to the Dn. First of all, 1, Qi must be 1 of the Pj, right? If D divides A, then it can't have any extra primes. Like all of the primes inside the prime factorization of D must also be inside the prime factorization of A, right? Do we agree with that? Right. So an example over off to the side is, let's say I have A is equal to 2 times 3 times 11 times, what's a better prime? 31's prime, I think. Is 31 prime? Someone tell me. 31's prime. Okay, great. And then let's say D is equal to 2 times 3 times 17. Can D possibly divide A? No, D cannot possibly divide A because there's a prime on the prime decomposition of D, which is not present on the prime decomposition of A. Since there's no 17 anywhere on A, D cannot divide A. You can see that immediately. That's like one of the powerful things that you get from a prime decomposition. You get these rules of divisibility and things like that. Okay, so if D divides A, then I need all of the primes on the prime decomposition for D to be part of the prime decomposition of A. And moreover, all the powers have to be less than or equal to the powers on A. For instance, if I had D squared, or not D squared, if I had 2 squared times 3, can this divide A? Now all the primes in the prime decomposition of D are primes in the prime decomposition of A, but so it's close to the intersection of the prime factor sets, but it's not quite the intersection. And we'll see that in a moment. My question here is, can D divide A?
Yes. Wait, no.
Right. The answer is no, because D is divisible by 4 and A is not divisible by 4, right? A is only divisible by 2, but it's not divisible by 4. If it were divisible by 4, it would have a 2 squared in there. So D has a higher power on one of the primes, and A has a lower power on one of the primes, so D can't divide A. So the second thing that I need for D to divide A is that if Qi is equal to Pj, then Di is less than or equal to Aj. This is just saying that the powers have to match up nicely. Okay, so now we can get to this intersection of primes idea. Here is the result. Let A be equal to, well, we're going to write it as a prime decomposition. So P1 to the A1 all the way up to PK to the AK. And B is going to be equal to, now I'm going to write this in a special way. So P1 to the A1 all the way up to B1, sorry, PK to the BK. And here I'm going to say the list of primes, P1 through PK, contains all primes appearing in the prime decomp of A and B. So let me give you an example of what I'm writing here on a new page. For instance, if I have A is going to be equal to, I don't know, 2 cubed times 11 squared times 13 times 31. And then B is going to be equal to 2 squared times 11 times 13 to the 100 times 31 squared, I guess. No. This is bad. I didn't mean to do this. Times 17 times 101 squared. Okay, so I've built two different numbers with two different prime decompositions. What I'm saying on the other sheet is I can also write A now non-uniquely as 2 cubed times 11 squared times 13 times 17 to the 0. This is the same thing as 1 times 31 times 101 to the 0, right? Now I'm rewriting A in a way such that all of the primes for either A or B are represented, and I'm allowed to have a prime to the 0. So note, this is no longer a unique expression, but that's fine. And similarly, now I'll have B is equal to 2 squared times 11 times 13 to the 0 times 17 times 31 to the 0 times 101 squared. Now is it more clear what I was writing with all my notation? So I'm basically, oh, go on.
It's clear what you're saying. I just don't understand the purpose of doing it.
I will get to the purpose in 5 seconds. Once you are happy with what I'm doing and how I'm writing, like if I take two numbers, I can write out a prime decomposition where all of the primes in either of the numbers are represented, and I just put a 0, I raise the prime to the 0 if the prime doesn't appear in the prime decomposition of A. Are we okay with this? Yes? Okay. Then my claim is that the GCD of A and B is equal to P1 to the max, or sorry, min, of A1 and B1, all the way out to pk to the min of AK and BK. In other words, once you list both numbers like this, where they have the same primes appearing in the list, then to get their GCD, what you do is you take the minimum power on each prime. So in this exact case, GCD of this copy of A and B is going to be equal to, what is the minimum exponent of 2 which appears? Right, there's an exponent of 3 and an exponent of 2, and we take the smallest one, so 2 squared. Now for 11, what's the minimum exponent of 11 which appears? Well, I have 11 squared and 11 to the 1. The minimum of 2 and 1 is 1, so I take a copy of 11. I've got a 13 to the 1 and I've got a 13 to the 0, so I take 13 to the 0. That's the minimum. Similarly, I have 17 to the 1 and 17 to the 0, so I take 17 to the 0. I have 31 to the 1 and 0, so I take 31 to the 0. And then I have 101 to the 0 and to the 2. I take the minimum times 101 to the 0. Or in other words, the GCD is 2 squared times 11 in this example. Now, is it clear why we wrote out these numbers in this fashion? I mean, it's a little artificial, but I just wanted to kind of let you know what this meant. It means we list all of the primes in either A or B, and some of the AIs or BIs are permitted to be 0. So the minimum of 0 in some positive integer is just 0. Excellent. I'm very happy to hear that. So the claim is that P1 to the min of A1, B1, all the way up to PK to the min of AK, BK. First of all, this divides A and it also divides B. And this is okay, right? Do we agree why this integer divides A, which is equal to P1 to the A1, all the way up to PK to the AK, and P1 to the B1, all the way up to PK to the BK? This must divide this because every power appears with, or every prime appears to a power less than or equal to how it appears in A. And similarly, every prime appears to a power less than or equal to the prime BI. And moreover, it is the largest number dividing both. And you can check that by saying if another number divides both, then it has the same list of primes, and then you show if any of the primes has a number larger than the min of A1 and B1, then it doesn't divide one of either A or B. Should I prove this rigorously? Or are we kind of comfortable with what GCD is and what?
I think it makes sense.
Makes sense?
With what you're doing now.
Cool. I think, yeah, it's more fun to prove things with this expression. Oh. Yeah, once you have the fundamental theorem of arithmetic and you understand what it means to divide something else, I think it kind of makes sense. And the key is just to apply the fundamental theorem of arithmetic everywhere, right? When you're looking at GCD of two random integers, it's like, I'm not sure. But if you, instead of two integers, you write two prime factorizations, then it becomes very clear what to do, I think. Moreover, it is the largest number dividing both A and B. Okay, so there's a very related definition, and these two kind of go together in a pair. So the next definition is the LCM, or the least common multiple. So the definition of the least common multiple is that if A and B are positive integers, the least common multiple, the smallest number divisible by both A and B is the LCM. So the greatest common divisor is the biggest number that divides A and also divides B. The least common multiple is the smallest number that is divisible by A and divisible by B. So there's a very similar way to think about the least common multiple. So if, once again, we have A is equal to P1 to the A1 all the way up to PK to the AK, and B is equal to P1 to the B1 all the way up to PK to the BK, what do y'all think the LCM should be of A and B in terms of this prime factorization?
Would it be P1?
So P1 is going to appear. So for instance, in this case, if we're looking at this copy of A and B, I'm looking for the smallest thing that is divisible by both of these numbers. So we're definitely going to have to write out some expression involving all of these primes. Maybe we should do a smaller example. Something like, let's say A is equal to 2 squared times 17, and B is equal to 2 times 3 squared times 17 squared. So I need a number which is divisible by both A and B. So if a number is divisible by A, that means its prime factorization has to include 2 squared and 17, right? Yes, P1 to the max AB will be the thing to put on P1. But do we agree at least that if a number is divisible by 2 squared times 17, it needs to have at least a 2 squared and a 17 inside its prime factorization?
Yes.
Right. And then if it's divisible by B, then it needs to have at least a 2, at least a 3 squared, and at least a 17 squared inside its prime factorization.
Yes.
Right. So the LCM here would be 2 squared, namely the highest power. So now it's divisible by both the 2 part of A and the 2 part of B, times 3 squared. So now it's divisible by the 3 part of B, and I need a 17 squared. So now it's divisible by the 17 part of both B and A. So in other words, what this process actually is I'm taking the maximum power each time now. P1 to the max, A1, B1, all the way to PK to the max, AK and BK. So now we kind of play this game in the other direction. It's clear that P1 to the A1 all the way up to PK to the AK divides P1 to the max A1, B1 all the way up to PK to the max AK, BK. Because you check, if you want to think about dividing, you check each prime, and as long as the power of the prime over here is less than the power of the prime over here, then it divides. Well, A1 is always less than or equal to the maximum of A1 and B1. And that's the same for every prime, right? A to the AK is less than or equal to the maximum of AK and BK. And it's the same thing for P1 to the B1 all the way up to PK to the BK. This also divides P1 to the max. A1, B1, PK to the max, AK, BK. So we know that when we do this construction, we know that we've built, so I would hesitate to talk about intersections and unions. It's clearly very close, but you're kind of doing two steps. You're doing an intersection or union on which primes appear, but you're also doing something involving the powers of the primes. But you're correct that in a general way, it is right to think of the GCD as an intersection and the LCM as a union. As long as you are unioning a bunch of primes together to the same power. Do you know what I mean? I don't know what a multiset is, so maybe. Probably. I think maybe the more important thing is to think of primes plus the data of multiplicity. So I don't just think about primes floating around, but I think of primes to a certain power. And that's what I'm intersecting or unioning. But it is correct that intersection and union are the right way to think about this later on when you get to what are called ideals. But I don't want to talk about that. How are we doing with this? Is this reasonable? Good, I'm happy to hear that. Should I do another example maybe? Yeah, let me do another example. Actually, yeah, let me do another example. Well, to do a good example, probably, I don't know what a good example looks like. Let's have A be, let's stop having 2. Let's have 3 to the 5th times 7 to the 12th times 11 squared times 31 to the 7th times 101. That's a reasonable number. Let's have B equal to 3 squared times 5 to the 10th times 7 to the 8th times 11 times, what's another prime? 13 squared times 31 to the 5th times 101 squared. I've been kind of fanciful with these. Oh, this is kind of less fun because all the primes here appear here. Can someone give me a prime bigger than 101? $131. Is 131 prime? Really? To the 6th. All right, if I've lied, it's not my fault. Okay, so let's find the GCD of A and B. So what's the GCD? When we go through the GCD, we're going to look at prime powers. So what is the smallest prime that appears in either list? Well, it's 3. And then I'm going to take the minimum power. So it's going to be 3 squared. The next part of the GCD is 5. 5 appears here to the power of 10 and here to the power of 0. So we're going to take 0 5s, 0 powers of 5. Next, 7 to the smallest power that appears is 8. The next prime up is 11. Smallest power is 1. Next one is 13, but 13 appears here and doesn't appear here. Or in other words, there's a 13 to the 0 here. So we'll take the 13 to the 0 instead of the 13 squared. Then we take 31 to the 5th. Then we take 101. And then we take 0, or we take 131 to the 0. So here's the GCD. We okay with that? Okay, now y'all tell me the LCM. I wish I could play like elevator music for y'all right now. As someone hopefully is writing down the LCM of these two numbers.
Should we type it into chat?
No, you should just say it.
Okay, I got 3 to the 5th times 5 to the 10th times 7 to the 12th times 11 squared times 13 squared times 31 to the 7th times 101 squared.
101 squared times 131 to the 6th.
Okay.
Yep, you just take the bigger number in each case. Good work, Alyssa. Okay, now we come to a, yeah, it is kind of long. That's why saying things is better. Now we come to a fun little theorem, or a lemma. A times B is equal to, well, here, let's think about A times B. A times B, you're going to take all the primes, and you're going, if you multiply things together, that means you're just adding up the prime powers, right? So for instance, A times B is going to have a 3 to the 8th, and a 5 to the 10th, and a 7 to the 20th, and an 11 to the 3rd, and a 13 squared, and a 31 to the 12th, and 101 cubed, and 131 to the 6th, right? You just add up all the powers. But the point is, for any two numbers, let's say K1 plus K2, I claim that K1 plus K2 is equal to the min of K1 plus K2, oh, sorry, min of K1, K2, plus the max of K1 and K2, right? Either they're different, either K1's not equal to K2, and then the min of them is one of them and then the max is the other, or K1's equal to K2, and then the minimum of K1 equals to K2 is just K1, and the maximum of K1, K2 is just K2, right? So K1 plus K2 is equal to the min of K1 and K2 plus the max of K1 and K2. But what does this tell us? Yeah, A times B is equal to the LCM of A and B times the GCD of A and B. That's kind of cool. And the proof is just this, really. And by that I mean the proof is a well-written, 4-line, well-written proof. But the idea is that if you add the min of a pair of numbers plus the max of a pair of numbers, it's just the sum of the numbers. This is a little corollary. That's nice. Any questions here? It is kind of cool. Okay, so now what we're going to do is we're going to do another old thing called the Euclidean algorithm. This pen is just killing it today. Okay, Euclidean algorithm, and this is what's the point? The point. Prime factorizations are hard. It is, despite the fact that we have a way to find prime factors by only needing to look up to square root of n, it's still really hard to find the prime factorization of a number. So we want a different way to find GCDs besides finding the prime factorization of each number. So find GCD without finding prime decompositions. And here is the thing to notice. So idea. Let's consider GCD of A and B, and let's assume that A is greater than B. Now I write out via the division algorithm. What should I write? Yes, in this case, A is equal to BQ. Here's the divisor, B, and Q is the quotient, plus R, where 0 is less than or equal to R, which is less than B. So I'm writing, if A is greater than B, I'm applying the division algorithm to A and B, and I have some remainder R between 0 and B. Now my claim is that the GCD of A and B is equal to the GCD of B and R. So the way to show this is to show that every number that divides A and B also divides R, and similarly to show that every number that divides B and R also divides A. So the collection of numbers dividing A and B is the same as the collection of numbers dividing B and R. So the largest number on one list must be the same as the largest number on the other list. So show if D divides A and D divides B, this implies D divides R. So this will be one step. But if if D divides A and D divides B, so if D divides A and D divides B, then D divides A minus Q times B, right? This is one of our first rules about divisibility. If you divide one number and you divide another number, this was the whole like D dividing, I don't know, K1, D dividing K2, then D divides mk1 plus nk2 for all integers m, n, and z. So I'm using this to say if D divides A and D divides B, then D divides this linear combination of A and B, but this is just equal to R. Okay, so I've proved that if D divides A and D divides B, then D divides R. I also want to show, so this is one point, another point, if D divides B and D divides R, I want to show D divides A. That's the same argument. If D divides B and D divides R, then D divides BQ plus R, which is equal to A. So essentially, what I've shown here is that dividing these two is the same as dividing these two. If a number divides these two, it divides this. And if a number divides these two, it divides this. So since the greatest common divisor is the largest number that divides these two, well, it's also a number which divides these two, and it must also be the largest, because if there were a larger number that divided these two, then that larger number would divide A and B. Do we agree that the GCD of A and B is equal to the GCD of B and R? Some hesitation and some silence I am hearing. Can I repeat the question? So does this sketch of a proof convince you that the GCD of A and B is the same as the GCD of B and R, where A, B, and R are related via the division algorithm? Okay, great. So what this does is it provides us a way. So another thing to notice is that here we had a pair of numbers, A and B, where A is larger than B. And we've replaced the question of the GCD of A and B with the GCD of B and R, where now R is less than B, strictly less than B. So I have reduced the problem to a smaller pair of numbers. And if I do that, I can do this again and again and again, right? So let me do an example actually of using the division algorithm. So let's do, let's find the GCD of 1331 and 1001. So the point is, I can always write 1331 as being equal to 1 times 1001 plus 330, right? So here is my A, here's my B, and here's my remainder. So I'm going to write a little triangle over here. 1331, 1001, and then here's the remainder is 330. So what I know is that the GCD of 1331 and 1001 is the same as the GCD of 1001 and 330. So now I'm going to make a new pair. I'm going to write 1001 is equal to, and now I do the division algorithm on this pair. Well, it's equal to 3 times 330, right? This is going to get me 990 plus 11, right? So now I make another triangle just for my own benefit. 1001, 330, and then the remainder is 11. So now I know that the GCD, let me write this, GCD of 1331 and 1001 is equal to 1001 and 330, which is equal to 330 and 11. So I'm making the problem easier each time because the GCD of 330 and 11 is easier to find. So I continue. I'm going to apply the division algorithm to 330 and 11. Well, 330 is equal to, let's see, 30 times 11, plus 0. So now what do I have? Now I have 330 and 11, and the thing down here is 0. So my last question is, what is the GCD of 11 and 0? Right? Here are the GCDs that are equal. This GCD is equal to this GCD. This GCD is equal to this GCD. And then this GCD is equal to this GCD. But now I've gotten it down to 11 and 0. What's the greatest common divisor of 11 and 0? Yeah, it's 11. Once you get down to a GCD of a number, so GCD of any n and 0 is just equal to n. So what I've done here is I've pretty efficiently found the GCD of two large numbers without finding their prime decompositions. And I don't know what their prime decompositions are, and it would be kind of painful to find the prime decompositions of these numbers. But finding their GCD in this fashion only involves multiplication and subtraction and doing the division algorithm, which generally is much easier. To solve the Diophantine equations. I believe you can, yes. I believe it's used for solving Diophantine equations. I'm not exactly sure I could cook up an example right now about that, though.
Where did the GCD of 11 and 0 come from?
So that comes from one of these legs of the triangle. So the theorem that GCD of A and B is equal to GCD of B and R is saying that whenever I write A is equal to BQ plus R, I make a little triangle that has A, B, and R. And now the GCD of these two is the same as the GCD of these two. So all that I was doing repeated applications of the division algorithm with the smaller of the two and then the remainder. So finally, what I got here was that 330 is actually divisible on the nose by 11. So the remainder is 0. So
that makes sense.
The claim is that the greatest common divisor of 330 and 11 is equal to the greatest common divisor of 11 and 0. That's why I make these little triangles. They make things, they organize my life, you know. They're not actually needed, but they organize my life. Can we do an example where the GCD is 1? Yeah, sure. Let's find the GCD of 100 and 101. Okay, I'm going to do the division algorithm. So I've got 101 is equal to 100 times 1 plus 1. Okay, so I've got 101, I've got 100, and then I've got 1 as the remainder. And now I have the GC, so now I write 100 is equal to 100 times 1 plus 0. So now 100, 1, and the remainder is 0. So the remainder here, GCD of 1 and 0, is just 1. That was easy. Admittedly, you can stop a little earlier with all of these things because the moment that you have a remainder of 1, it's over, because the greatest common divisor of 1 and any integer is always 1, right? GCD of 1 comma n is equal to 1. So how are we doing with this Euclidean algorithm? Yeah, it's kind of fun. So time's up for class. I will meet with people in office hours to discuss questions 10 and 12 on the homework. And then what we're going to start next time is chapter 9 on equivalences and relations. So that's cool. Have a
Our
nice
office
day,
hours
everyone.
in the same room.
Oh, what's that?
Our office hours in the same room.
Yep, I'll just leave for like 15 minutes and then come back to the same room.
Okay, cool. Thank you.
Thank you.
Have a nice Monday, everyone.